one more minute to see how many more are coming in. Obviously, it's very hard to start a session straight after an event like last night's Harbour Cruise. I believe it went quite well. Did it, Greg? I get there all right. Unfortunately, I couldn't get there. I'd flown overnight from Tokyo yesterday, and by 4 o'clock in the afternoon, I was seriously nodding off. But this morning's plenary presentation is my honour to introduce Professor Gordon Wyeth from Queensland University of Technology, which for those of you who don't know much about Australian geography, that's located in the city of Brisbane, the capital of the state of Queensland, just about north. Professor Gordon Wyeth is head of the School of Electrical Engineering and Computer Science and Professor of Robotics in QUT. Prior to 2010, he was at the University of Queensland, which is also in Brisbane, where he was co-director of mechatronic engineering. Professor Wyeth's main interests are in spatial cognition and biologically inspired robotics, with more than 150 papers published in journals and conferences. He has served as president of the Australian Robotics and Automation Association from 2004 to 2006, chaired the Australasian Conference on Robotics and Automation in 1999, 2004 and 2011, chaired the IEEE Robotics and Control Systems Queensland chapter 2010 and 2011, is currently a reserve member of the Australian Research Council College of Experts. So I'd like to invite Gordon to make his presentation.
Thank you very much, Chris, for that very kind introduction. And thank you all for backing up after a late, very enjoyable evening with a quite remarkable fireworks session last night. And we're making it here this morning to hear this presentation. My name is Gordon Wyeth. I'd like to acknowledge right up front the work of my collaborators, Michael Milford, and PhD student Will Madden in a lot of this work. QUT is where I'm at the moment, but as Chris mentioned, I do a lot of this work also at the University of Queensland. And this work's been generously supported by the Australian Government through the Australian Research Council. So this work really started by trying to understand how a rat navigates, and some of the work that's been done in understanding how rats navigate really comes down to what you're seeing here in this video. So in this video, there's a rat inside a circular arena, and it has a probe stuck in its head. Now that probe actually is a piece of wire that's surgically implanted down into a part of its brain called the hippocampus, or a region of the brain called the hippocampus. Now, you'll notice that there's some noise going at the moment. Now, that noise is the sound of the neural cells that are firing within that particular region of the brain. So the game here is to spot the correlation. How does the rat's behaviour correlate with when the sound goes off? Now the hint is that there, in the cap on the rack there's in fact more than one LED. There's a red one and a green one indicating orientation. And if you look carefully, you'll see that the noise only comes when those LEDs are arranged in a particular direction. So the sound's not correlated to where the rat is particularly within that arena. The sound is only correlated with the direction that the rat's head is pointing. Now this is a remarkable piece of information, that inside a rat's head there is a compass that relates to global direction. And in fact what we find out is that if we go and probe other parts of the rat brain, there are all kinds of cells that are encoding space, that are providing positioning information. Probably the most well known of these are the so-called place cells. And the place cells indeed do fire at a particular place. So they fire at a particular place and they don't particularly care so much about direction. So this is an idealised place cell and the way that it would behave. The head direction cell, that was the example in the video that we just put up. So it doesn't care about place, but it fires with respect to a particular direction. And then there are some very interesting cells that are found. This is a quite recent discovery. About 2005, 2006, this work was emerging, where there are grid cells. And grid cells fire with a particular tessellate pattern. It's always obeys this equilateral triangle tessellation, or you could perhaps look at it as more broadly a hexagonal tessellation in terms of the pattern across place. Some of them have no head direction properties, some of them have head direction properties. So, when you look inside a rat brain, and rats are remarkable navigators, rats are astounding navigators. Given the information a rat has, we could not build technology to match their performance and understanding where they are and how they, and remembering how they want to go, where they want to go. Rats can have range up to 1 or 2 kilometres in the wild, with many paths through the environment, and they don't get lost. The domestic rats that we use in experiments, we don't experiment over such large ranges, but again, they have remarkable and very powerful navigation points. So these are good brains to study. And the thing that emerges from this biological work is that rat brains undoubtedly track the pose of the rat. There's an X, Y, theta code in there in terms of a global reference frame so that the rat knows its position. In terms of understanding that pose, this isn't as simple as having, for instance, some sensory input that says, oh, I can see this, therefore I'm here. It's not driven by sensory input. If you completely deprive the rat of all sensory input, it will still have a notion of where it is in space. Obviously, that will become more and more erroneous over time with a lack of sensory input, but it will still have a notion of where it is in space. So it maintains this code. It is a measure of state. The rat can update that state information, that pose information, purely from odometry. I'll call it odometry. I'm a roboticist. Okay, I'll call it odometry. What the rat's actually using is some notion of how much its feet are moving, how much its head's moving from vestibular information, accelerometer information. So it's able to update this code without looking at any other global reference frame. But when a rat has access to some kind of landmark, then the rat can use the landmark to reset the kind of error that we know as people who work in localization and navigation. We know that if you're using odometry to keep track of where you are, you're eventually going to build up error. It's an integration process with bias, so you're going to end up with error. And a rat, as we'd expect, uses landmarks to correct that error. And you can perform tricks on the rat. You can move a landmark and watch it correct its error in the wrong way based on the way that you move the landmark. So these are approaching, I guess, biological facts. And biological facts I've learned over the years are few and far between. They are mostly theories that are things that are to be argued about. But these are approaching facts. Much more speculative then would be a wiring diagram of what goes on inside a rat's brain. And indeed you can look at some very good work that breaks down different regions of the brain and how they're connected. And there's people who are studying microscope slides dyed with different colours and so forth in terms of working out where different tracks go. I'm just going to talk about the wiring diagram in the broadest sense. rat brain. There's a part that processes this odometric style of information, combining footfall information with vestibular information, and I've called that the self-motion cues. And there's obviously a whole part of the brain that deals with global sensory information. How does the rat know where a landmark is? A landmark for a rat can be many things. It's not going to be, seeing Big Ben and knowing it's in London. It's not that kind of visual landmark. A lot of the times it's smell. 3% of the rat genome is tied up with olfaction. They are very big on smell. It's one of the major cues that they use in their life for all kinds of things, and it has a role in localization. Rats also use their whiskers. They can see to some extent with their whiskers. And there's regions of the brain that combine all this information to try and create landmark snapshots, which take in very proximal information as well as distal information to put together a set of cues to say, this is where I believe I am. Looking at the wiring diagram, these grid cells that have been more recently discovered sit somewhere between the head direction cells that encompass that bearing type of information and the information that describes place, where the rat actually is in terms of where it's able to go. So, in our work, what we're interested to do then is to take that level of biological information and turn it into something useful. I mean, we've done this work. This work expands in both directions. From the middle ground of working with biologists, teams of engineers and biologists, we work in two directions. For the most part, I'm going to talk to you today about the work we've achieved in localization and navigation and the engineering direction we've gone. But I'll just touch over some of the work we've done with the biologists and try and explain the foundation of these models, because they're a little bit different to the usual tools that you might be familiar with. The fundamental computational model that underpins a lot of our work under the title RatSLAM is the notion of an attractor network. So in an attractor network, we come back to this notion of units, and I'm doing an example here of the head direction network, the video that I showed you, cells that fire in association with a particular angle. Okay, we can expand this same notion out to grid cells and out to place cells as well, and I'll explain that briefly in a minute. But I'm just going to work through the one-dimensional example as being perhaps the simpler one to work with. With a head direction network, let's suppose then we have a group of units. Obviously, they're not arranged in convenient circles like this in the rat brain, but there would be an array of units that quite equally represent the different points around the compass. So if we consider these, just unwrap them for the minute, and start to think about how these might be wired up with this notion of the first problem of how can you get a set of units to remember things. And units, neural units, we understand their fundamental properties, their, I don't think we want to get too tied up with neural network type literature, that's not really where we play. But just this notion of a neural unit being some kind of dynamical element, a first order dynamical element, an RC network in electrical engineering terms, or a mass with friction in mechanical engineering terms. So you provide a degree of input and it will approach a steady state. So when we look at wiring up these units, then we want the output of one unit to affect another unit. So the bold line, the thicker line here represents a strong connection, the thinner line represents a weaker connection. And you can see how this kind of wiring diagram would tend to maintain state. A unit that is currently excited will tend to self-excite and it will support those nearby as well. And that is then balanced by a notion of global inhibition, so that all of these units will tend to balance out or compete with each other. So the lines here that have a little circle on the end indicate some kind of inhibitory connection. And there's some evidence that these principles exist in the biological wiring in the appropriate sections of the rat brain. That wiring is, of course, repeated for every unit. So, Let's have a look then at how that type of wiring might behave, and indeed this is supported by the evidence that we get from the recordings from rat brains. A rat, interestingly, isn't big on supporting multiple pose hypotheses. In terms of remembering state, a rat will converge on one state. It won't maintain competing pose hypotheses unless it is getting strong evidence that there are confusing evidence. In the absence of any evidence, a rat will tend to collapse down to one hypothesis. That's very different to the way that most of the probabilistic localization algorithms work. Engineers generally work on the principle that you keep all of your hypotheses until you get some evidence to refute or strengthen them. Rats don't. They, I think, seem to have the underlying prior that I can only be in one position in the world, therefore I should collapse down to one position. That seems to be what evolution has produced. So in terms of our wiring diagram then, the effect of the local strong connections and the global inhibitory connection is that if I had two competing hypotheses like this, that one of them would be strengthened and one of them would die out. And that we go from having these point attractors now to having some kind of larger attractor, where we have a population of cells on either side of the hypothesis that are also weakly activated. And this corresponds to the kind of things we see inside rat brains. Now, the trick then comes down to how do you actually integrate odometric information. And there's some interesting information that shows that there are both excitatory and inhibitory connections that are coming from that are connected up to the units that indicate self-motion. So in this case, if we've got some self-motion cues that indicate positive rotation, then the units that indicate an increasing angle will become more excited, and those that indicate a decreasing angle will become less excited. How could this be? How could a brain wire itself up like that? That was a question that we asked ourselves some time ago. Without going through all of it, when you actually get down to some of the more detailed properties of these units, you can actually show that rats constantly are self-calibrating their mechanisms of odometry. It isn't set and forget. It's actually constantly recalibrated in the way that these connections are worked out. And it's not just the role of the simple level of activity leads to level of output. You actually get down to the properties of the individual spikes that go on inside these neural units to make all this happen. So there's some really, going in the biological direction, there's a lot of work that we can show with our computation models that contribute, for instance, this publication into the broader biological literature. Of course, with this kind of wiring, if we excite to the right of the packet there, it's going to tend to move across, and we're updating our representation when you get the cues. And there's matching sets of right-hand, left-hand type of rotation. So, that's points 1 and 2, the three things I said about postcode. 1, we have a system for remembering, a system for maintaining state. 2, we've got a system for integrating odometric information into the state of the rat. Now, this is really appealing as an engineer, right? We're building it to understand. We're modelling this biological system. Can we do the third one then? And the third one then is the use of landmark cues, this use of combined sensory information to say, oh, I visited a place I've been before, therefore I must be here. So in terms of our head direction network then, we work with a model where landmark cues excite what's called a local view code. Biologists call this a local view code. So based on all the sensory information that you might have, you come down to a local view which says, this place has an appearance of, let's say, class A. We don't expect these local view codes to be completely lacking any form of aliasing. Right? There might be several. If you were walking down a corridor and you were just using sensory information, there are many places inside a building that might look very much the same. And this is the well-known problem of appearance aliasing if you're using some kind of appearance-based technique. And as far as local view cells are concerned, sure, all they're doing is really breaking up the kind of sensory information that the rat receives to say that this is appearance of class A, and it might appear at many places within the environment. And of course, there are many such classes of landmark cues. Again, in reality, in the rat brain, the algorithms for doing this are another interesting thing to unravel. I'm not going to talk about it today, but again, it comes back to this spoke timing distance and the real details of the way that these neurons work. The lumped models that neural network literature in general are happy to use sometimes aren't so useful. Getting down into the spikes gives you a lot more computational power. And again, some interesting work there that we've been able to inform the biology. So, if you have then a set of landmark cues associated with a particular local view, and at a particular time we see that local view, and there's a level of activity sitting inside our neural unit centered around 120 degrees, the algorithm is very straightforward from a computational sense, heavy in learning. If there's activity on both sides of the connection, make it stronger with some notion of saturation. It's a well-known computational algorithm. There's a bit more to it when it comes down to real biology, but that's the fundamental notion. So the process of recalibration then comes down to, let's suppose I've come back to the same place where I'm seeing the same landmark cues, but my current position hypothesis is something different. If I've previously made these connections, I'm going to inject some energy into this attractor network. Remember, all the other connections are still there, right? It still has this property of global inhibition, local excitation. And so what you'll find then is that the activity packet will correct back to the point where the rat saw this appearance in the past. The appearance might come from vision, olfaction, whisking. It'll also start to build some weak connections out to, those two things might actually be the same. I might be aliased. I might use this local view in more than one place, as it turns out. Okay, so that was working through the principles then of the way a rat maintains pose, remembers pose, maintains pose with odometry, and updates its integration over time with landmark cues in a one-dimensional sense. You can build these attractors in 2 dimensions. It doesn't take much imagination to take my wiring diagram there in a straight line and to put it in a grid. And indeed, if you put it in a grid and measure the activity, you can do the same kind of trick where you add some integration, a particular velocity and direction, and the activity packet within our model. And again, I'm not implying that rat brains are laid out in neat grids like this. I'm just saying that there are units that represent different parts of space. Yeah? And if we did organise them like this, we would see activity described in this way. We can achieve our path integration, and we can also do things like local view calibration, where we can inject energy into a particular place that will compete with other activity with that one. So, okay, rat brains can compute. Nice. Bit of a problem with that grid, and this is pointed out by Bruce McNaughton, that if you had a rat brain that was really had a set of units that was arranged for X and Y, what happens when you reach the boundaries? Does the rat just have a set of units that deals with, well, as much as this room, but then if it falls off the edge it gets lost? Don't think so. In fact, we can show that it doesn't. So the notion that McNaughton had is that there should be some kind of wraparound connections where all of those units are locally connected, right, with local excitation. If you wrap around the edge units so that one edge locally excites the other edge as well, then you never fall off the edge. You'll just wrap around and keep going over and reusing your set of cells. And so you can think of basically grabbing that plane, wrapping it around into a cylinder to bring those 2 edges together, grabbing it and bringing the other 2 edges together, and now you've formed a torus. as being actually a representation of what's inside the rat's brain. And that would stop the rat from falling off the edge. So what happens if you do that? Interesting, we end up getting a tessellated version of the recording. Now, if you just do the torus in the way that it's described by McNaughton, you end up with a square tessellation. We went a step further, and I'll show you that in a moment. But it's starting to look a bit more like those grid cells. It seems to be a step in the right direction. So, I've stepped through, I hope, without getting into too much detail, the way that rat brains work. And we have these population of cells, we have a way that they're connected. Our interest is to make a robot work better. And to that end, we build a system called RatSLAM. Now, in RatSLAM, we've really started to play around with the notion of head direction and grid cells, combine them together into a computational structure we call pose cells. And pose cells end up looking a lot like what these grid cells that were actually discovered in parallel in the rat at the same time as we were inventing their need in our robot. So in a robot, wheel odometry gives you self-motion cues. That's easy. You could also use get your odometry from vision. We've done that too. Pose cells. So what we figured you really need in order to track pose of a rat, it isn't X, Y in one place and theta in another. You've got to bring X, Y, and theta together because all of those variables are tied together in the way that the rat moves through planar space. Incidentally, rats are not 6DoF. Rats don't care about 6DoF. Rats are 3DoF. They have 3DoF brains. This has been proved in space. They've taken rats in space and done these kind of recordings, not our group, in the spatial to show that it's, regardless of gravity, vector, whatever, the rat still just wants to keep track of things in the tree-off. In our work, we took this idea of a plane wrapped into a torus and went to a cube wrapped into a hypertorus. So you can think of each of those faces now being connected together, and if your brain works in 4D space, you might be able to visualise a hypertorus where all the sides of that cube join together. Don't try too hard, it starts early in the morning, someone will get hurt. So, if you then think of now having, instead of these circles of activity, we've now got spheres of activity inside our tracking network where it's connected in the way that notion of hypertorus, you end up with a tessellation like this. You actually end up with the hexagonal tessellation, which is mimicked very strongly. So remembering that we published that one in 2004 and have been working on it ever since. This was the grid cells that came out in 2005, complete fluke. It was just reasoning through what a rat would need to be useful as a robot. We ended up with the same tessellated pattern that you see in the rat recording. Of course, we didn't realise the similarity until much later, and of course we made our diagram use the same colour map that the well-known Nature paper. So, the other part of the trick then is how do you do useful visual data association? If we're going to use calibration, I don't want to build a robot that has whiskers and a robot that can smell. That sounds far too hard. Visual data association, when you use this kind of technique, can be very, very simple. In fact, we've shown it can work with as little as 2 pixels. Right? We can localise from 2 pixels. Typically, we use an image where we take either a forward-facing image or we may use an omnidirectional image, and we subsample it right down to be a couple of hundred pixels, typically. And our matching process is extraordinarily simple. Where, let's say, that's the current image subsampled down to 4 pixels over here on the left. I've got 3 previous templates, places that I've seen before. Perform a comparison between each of those templates. Subtract the pixels from the pixels.